Yeah, so the first talk is about Liftoff, so the new baseline compiler that we added to V8 quite recently. And I will start by, yeah, basically from the developer's perspective, which is maybe your perspective. So if you want to compile or instantiate a WebAssembly module, this is the, let's say, the most basic code that you might write to do that. It's not the best code. Let me say that clearly right away. We will later improve the code a bit, but this is the most basic code that you can use. So you would fetch some binary data, in this case, the module.wasm file. You get a response. Then you wait for the content of that response by this array buffer method. And then you feed that into the webassembly.compile method, which compiles a WebAssembly module for you and returns that. And then you feed that into the webassembly.instantiate method, which creates an instance, and you return that. So this code matches quite nicely what actually happens in the engine. So down there you see this timeline from left to right. And so we first fetch. When this is done, then we compile, and when this is done, then we instantiate. Right now, you might already have heard that this is not the best way to do this. So we can actually improve this a bit by combining a few steps. So in this case, it's actually one line shorter. So here we fetch the binary again, but we don't wait for the result of that. We just take this promise and feed it into the webassembly.compile streaming method. So that receives a promise that should resolve to a response. And then it compiles the data that comes in via the network. But the benefit is that we can now basically start compiling while we already download. So this is why it's called compile streaming, right? And in the timeline, you see that now the fetch and the compile phases happen at the same time. So while the data comes in, we can already compile it. And in this case, the fetch finished before the compile. So compilation takes a bit longer. If your network is slower and the fetch phase takes a bit longer, then we can actually hide all the compilation time in this fetch. So yeah, you might wonder how we can finish compilation before finishing the download, right? But so maybe we can't finish that early, but we can actually finish a bit before all the data is there, because at the end of the module, there are things like names for debugging, or the element section that's used to initialize the memory or tables. So if you have been here last time, Andreas showed a bit of the structure of the WebAssembly modules. And it is specifically organized such that the code comes quite early after some metadata, and then all the data that's not needed for compilation comes later. So we can actually finish all the compilation before all the data is there, and then we instantiate later. And now we can again combine the compile and the instantiate phase, and we save another line. So you can also take the promise and feed it immediately to webassembly.instantiate streaming. And yeah, this way we can actually theoretically already start instantiating before all the data is there. So that's the high-level perspective from a developer's view. Now, if we look into this compilation phase, which is the phase that we're interested most right now, then what happens is we decode all the individual sections of the module. And once we find the code section, we can actually start compiling. So we compile in the background and background threads. And of course, at some point, we will have to wait for all this compilation to finish before we can finish the overall compilation. So that's the high-level view of the compilation. And of course, the most heavy operation in here is compiling the actual function. So if we look into this, if we compile a function with the turbofan compiler, so this is the optimizing compiler in V8, then there are a lot of different phases. So it starts with decoding. So it's again, time goes to the right. So it starts with decoding the actual function body. At the same time, so while we are decoding, we are verifying. So this is mostly type checking. And then we generate the intermediate representation that turbofan uses. This is a sea of nodes, so it might look somewhat like this graph here. So it's just nodes that represent operations and values, and they are connected via edges. There are data edges, control edges, effect edges. So for example, if you cannot load a value before another store has finished, then this is an effect dependence between operations. And then once we have the sea of nodes representation, we run a number of phases. So we optimize a bit. So this might eliminate redundant loads or combine redundant operations. Then we schedule this sea of nodes, because we have basically lost the information about the order of the individual operations. So now we have to recompute this. So we have to find an order for all the operations in the graph that is valid, that fulfills all the dependencies that are encoded in the graph. After that, instructions are selected, then registers are allocated, and finally we generate code. So this is quite a long pipeline. It takes a lot of time. It also takes a lot of memory. So this intermediate representation can take about 50x the actual size of the raw WASM bytes, because we need to have all these nodes in memory and they are connected via edges. All this has to be represented in memory. So this is quite heavy. And in fact, if we look at the time that it takes to compile things, so just one example, this is an epic example. So for example, the Zen Garden demo that you might have seen. It has about 40 megabytes of WASM binary data. And compiling this with turbofan takes around 6 seconds on a good desktop machine. On an Atom processor, it already takes a lot longer, because there we have smaller caches and just lower frequency. So it's just a lower end processor. And on a Chromebook with an even lower end ARM processor, it currently takes with turbofan about 80 seconds to compile this Zen Garden demo just for compilation. So this is clearly too much, right? No one wants to wait for 80 seconds before the nice Zen Garden demo starts. So already last year, we thought about alternatives to speed up this compilation phase, so the startup phase. And one thing that we could do, and we actually tried this, is to just omit this compilation phase and do lazy compilation, right? So instead of compiling all the functions up front and then start executing them, we could actually just start executing the program, and as soon as we hit a function that has not been compiled yet, we just compile it. And if we try this, then, so the numbers before are the 6 seconds for compilation. And then at the same time, there happens this building shaders phase. So this is a number that the demo itself outputs. So this happens concurrently to compilation. And afterwards, there's this launching engine phase. So this is where the WASM code is executed. So it sets up internal data structures and stuff. So while this launching engine phase is running, you still don't see anything, right? So only after this, after about 21 seconds, the demo will actually start running, or you will see something. And with lazy compilation, this compile time, of course, goes down to nearly 0, because we don't need to compile anything. Also, this building shaders phase gets much shorter, because it doesn't. So compilation, building shaders doesn't block each other anymore. So all the CPU is there for building shaders. So we start executing much earlier, after 3.3 seconds. But then this launching engine phase takes a lot longer, because now, while the code is executing, we always need to compile new code. And this now only happens on the main thread. So whenever the main thread hits a function, it compiles it and then runs it. So only if it hits it for the first time, of course. But before, we had parallel compilation, right? And now we only compile on the main thread. So it takes actually a lot longer. And we have a lot of jank. So while the code is executing, there are always these pauses for compilation. So we don't want this. So this also breaks like the basic promise of WebAssembly with this predictable performance, right? You don't want this long compilation pauses during execution. So another thing we discussed is an interpreter. So this would be similar to the JavaScript setup. So there we have the ignition interpreter, which interprets the JavaScript code, and after some time, it decides to trigger turbofan compilation. We could do something very similar for WebAssembly, and we actually tried this and prototyped it. This is the example I will use throughout the rest of this talk. So it's a simple WebAssembly function that takes 2 int32 inputs and returns an int32. And what it does is, so when this function starts, the 2 input values or the 2 parameters are stored in the 2 local variables 0 and 1. So in WebAssembly, parameters and locals share the same index space. So actual local variables of this function would start at index 2. Here we don't have any, so the locals 0 and 1 are actually the 2 parameters that you pass in. And WebAssembly is a stack machine, so before using any value, you have to push it onto the value stack, and then operations consume from the stack and push back values onto the stack. So here the first get local 0 just reads the value of the first parameter, pushes it onto the operand stack, and then we have an if. This if consumes the value that has been pushed. And in this case, the if produces an int32 value. So when this if finishes, it should leave an int32 value on the stack. And now if this first parameter is not equal to 0, then we execute this get local 1. So we push the second parameter on the stack. Otherwise, we push the constant 32. And then we return that value that we pushed. So we return either the second parameter if the first parameter is not 0, and otherwise we return the constant 42. Okay, now if we would execute that code, or if we would just compile this code using an optimizing compiler, turbofan, for example, the machine code to execute this would look something like this. So the two parameters come in the registers RIX and RDX, and we basically test the first parameter. If it is equal to 0, then we jump down to the else statement, or the else label. And what we do there is we move the value 42 into the register RAX. This is the return register. So whenever a function wants to return something, it moves it into the RAX register, and then we return. And if the value, so if we don't jump to the else case, then we move the value that's in the RDX register into RAX, which is the return register, and then return. It's quite simple. Okay, and if we would execute the same code in an interpreter, so we would not generate this machine code, then it might look something like this. So for each single opcode, so for each single operation that WebAssembly provides, there is a special handler that knows how to execute this opcode. And we start by just reading the first opcode, in this case a get local, and we execute the handler for that opcode. So the handler gets two parameters. It's the PC, so a pointer into the binary data. So it points to this get local operation, and it gets a pointer to the stack. So it knows where. So this is a pointer basically above the top of the current stack. So it knows when it needs to push values onto the stack, it knows where to write them. Then what this handler does is, for a get local, it has this 0, which is an immediate value that is encoded in the binary data, and this is variable length encoded. We use this lab encoding, whatever it does, but it encodes an integer in between 1 and 5 bytes. So we have to read this. So this is what this decode lab does. It returns the index, in this case it would be 0, and the number of bytes. In this case it would be 1. If it's a bigger number, it would be more. Now we somehow need to read the value of this local variable. So, I mean, you don't have to understand the full code. Basically, what you have to understand is that this is a complex operation, right? So a lot of things happen for a simple thing such as get local. So we load the value from the actual frame at the index that we just read. Then this we assign to the stack pointer. So we write a value onto the stack. Then we compute where the next operation would be. So this is our own PC plus 1 plus the number of bytes that has been read for the immediate value 0. And then we need to find out what the next handler, or which handler has to run next, right? So for this, we have a dispatch table. So this is just a huge table that contains all the handlers for all the different opcodes. So we read from the PC. So this is the already incremented PC. So we read the next operation, which would be the if. We read which handler executes an if instruction. We load that, and then we just call it. So this last line, this is the tail call. So otherwise, you would run out of stack space pretty soon. So basically, we just jump to the next handler and pass the incremented PC and the incremented stack pointer. Yeah. So now after this, one short thing to note, this is not even the complete picture, as you can imagine. So in this case, we are assuming that we are loading an int value, right? You see this int encoded there. But actually, we can't assume this, right? A get local can load any value. It can be a float value or whatever. So actually, this get local handler would be even more complex. So we need some side tables and structure that we computed before, and then we need to load the actual type that we want to load from that side table. So even more complex. So then we jump to the if handler, and the if handler, again, pushes the value from the stack. So it reads from the stack pointer -1, so the top stack value. If that value is 0, it needs to jump to the else case. But where is that else case? It doesn't know, right? So we, again, need to have the side table, which contains basically the continuations for all of these opcodes. So for this if, it would contain an entry that tells where the corresponding else is, so it can jump there. Otherwise, we increment the PC by 2 in order to get to the next get local opcode, and then we dispatch again. And yeah, similar for the in32 constant. So this is one of the most basic operations, right? It just loads a constant to the stack. So in generated code, this mostly doesn't generate any code at all. And here we again have to decode a variable length encoded operand and push stuff to the stack and load from the dispatch table and call. So a lot of overhead. And if we, so as I said, we actually prototype this, so just a number like a dozen of instructions, so just the instructions we need in order to run very simple tests like this, a very simple loop. And basically all you need to know here is, so we have the number of iterations on the x-axis and the execution time on the y-axis. It's log scale. So we compare different execution tiers. So the top, so the yellow line, this is an interpreter that we have written in C++, an existing interpreter. This is what's being used for debugging, for example. So if you ever set a breakpoint in a Webassembly function and wonder why it gets incredibly slow, this is because we are interpreting it then. And the green line is our new interpreter. So it is 4x faster than the C++ interpreter. This is good, but it's still like 50x slower than the red line, which is turbofan compiled code. So yeah, in JavaScript, it makes much more sense to have an interpreter because in JavaScript, a single operation typically does way more than a WASM instruction does, right? So WASM instruction like loads a constant onto the operand stack. And in JavaScript, this is something like load a field from an object, which is a way more complex operation, right? Including prototypes and field lookups, and I don't know, Benedict can tell you more about that. Okay, so for WebAssembly, it seems that an interpreter doesn't really make too much sense. So what we decided to do instead?
Yeah, sure. This green new implementation, what kind of language did you use there?
So we implemented this very similar to the Ignition interpreter, and there each bytecode handler is implemented in CodeStub assembler. This is an internal assembler in V8 that we use to generate assembly code. So it's very low level, very close to the assembler.
So it's a domain-specific language. It's a domain-specific language just to generate. Yeah.
So it allows us to basically define each single handler in a platform-independent way, and then we compile it with turbofan into machine code, and then we use this machine code for the dispatch table. So all pointers to these different functions are placed in the dispatch table. More questions? So this is an interactive talk, so please feel free to ask questions. Oh yeah, sorry, I didn't mention that. The blue line is just for comparison the time that it takes turbofan to compile this simple loop. So it doesn't really matter what it does, so it also doesn't compute anything interesting. But so this is about, what is it, like 20, 30 milliseconds, always a bit hard to say on a logarithmic scale. This is just to see how many iterations we need to execute until we are faster, or until it takes longer than it takes to actually compile the function. Yeah. Okay, so what we decided to do after these experiments, or at that point we didn't decide yet, but we prototyped another thing, which is a baseline compiler. And by the title of this talk, I'm probably not spoiling anything if I tell you that this is what we then actually implemented. So we can also just call it Liftoff. So this is the design of the new baseline compiler. And the idea was to have a fast single pass compiler. So in comparison to this turbofan pipeline with a lot of phases, the baseline pipeline would basically just decode a function and immediately generate code. So as soon as we see a single bytecode instruction, we immediately output the code for that. So it's a single pipeline, like really streamed compilation, right? WASM binary in, code out. The register allocation happens on the fly. So whenever we hit some instruction, we immediately choose any register to use for storing the value in that register. So this is, of course, not optimal at all, but it just chooses any valid register allocation. And one constraint that we wanted to fulfill is that the code that Liftoff generates is compatible to turbofan. So in the engine, we don't want to handle two different kinds of code. So from the engine's point of view, the code would be totally compatible to turbofan. It contains all information that also turbofan generated code contains, like source positions, information for the garbage collector. What else do we have there? Other stuff. So whatever a turbofan annotates to code, also Liftoff should generate the same. So the engine can just treat them exactly the same. It would just be a bit bigger maybe and a bit slower.
So what does this end product look like? What is it? Is it bytecode? No.
The code that we generate, this is machine code.
So this is assembly, but like it should be compatible. What does that mean? I don't really understand.
So if we want to execute this code, if we want to call it, it doesn't matter if it's turbofan or Liftoff. So it has the same interface basically, right? And also if the garbage collector hits that code, so if it iterates your stack and it sees, oh, you're executing Wasm code, and then it looks up which code are you executing, then it doesn't care if it's turbofan code or Liftoff code. So all the information that turbofan generates is also generated by Liftoff. So that's meant by compatible. So it will contain a few more move operations because the register allocation is not perfect. But apart from that, it's the same. So for the engine, it doesn't complicate the whole engine, right?
And turbofan would also generate code from JavaScript.
Turbofan still is able to generate code from JavaScript, sure.
So you kind of end up with the same machine code, or same interface machine code, irrespective of. Yeah, so Liftoff will only be able to generate code from Wasm, right? And turbofan is able to generate either code for JavaScript or for WebAssembly. Yeah. And we only need to be compatible to WebAssembly code because Liftoff can only generate WebAssembly code. More questions? Okay. So I again want to go through an example how this would look like for the same function. So this baseline compiler keeps an abstract state. So it needs to know a little bit about the stack and where values are currently stored. So what it keeps is a stack of blocks. So this is currently just one block representing the function body. And it contains a representation of the stack. The stack also stores the local variables in this representation. So when we start the function, we will have two locals, and their value is stored in RAX and RDX. Each of these slots can later, during execution, also be spilled to the stack, or as a small optimization, if we load a small integer constant, we won't assign a register and load the constant to that register. We will just remember that constant on the stack. This optimizes a few things. If you're interested, I can talk about this later. So this is the state that the Liftoff compiler holds. And then when the function body decoder feeds it the instructions that it decoded, so it will start with a get local, then we will always update this state. So if we execute this get local, then Liftoff will look up where local number 0 is stored. It's stored in the register RAX. So okay, that register now also holds the first, or the only stack value, right? So we push an entry to the operand stack and remember that the value for that entry is stored in RAX. Now when we execute the if instruction, this if will consume the RAX or this value from the operand stack, and it immediately outputs some code. So it tests this RAX register, and if this is equal to 0, then it needs to jump to the else case. It doesn't know yet where the else case is, so this is an abstract label. This will be bound later. But it already emits the code containing this jump, and then we later patch in the address where it actually needs to jump to. Yeah, and that's it. And after the if, that's not it. What the if also needs to do is to update the stack of blocks, right? So the if opens a new block, so we push another block to this stack. So it's labeled with the if. And we keep the old block f, but it is now inactive. So the current state is now, or the current block is now this if. And we also need to kind of snapshot the current stack state, because we now start executing the body of that if. But if we later generate the code for the else, we basically enter that code from that same stack state, right? So we need to remember how the current state looks like in order to generate correct code for the else later. So we basically snapshot the current state and put it on this if block. And then we go on. So in the if block, we now load the local 1. So this is in the REX register. Fine, that's easy. And after this is done, now this if block so the first branch of this if is finished. So this code now needs to jump basically to the end of this if, to the first end. And we need to ensure that the code that we generate at that point sees the right values. So we somehow need to remember which stack state we are assuming at this endpoint. So what we do is we again snapshot the current state, but with one constraint. So here we are using the same register twice. So RDX is used for local 1 and for the stack value. And we cannot just copy the state, or we cannot assume that the same state is reached at the endpoint, because if someone else later jumps to the same state, or for example, this else branch that we still need to compile, right? It also wants to execute the code after the if. And if we use the same register RDX twice, then we can only have the same value in variable 1 and on the stack. And we cannot assume this. So we have to deduplicate the register. So in this case, we just choose the register RCX instead of using RDX a second time. Okay. And then since we now know or computed the state that we want to assume at the endpoint, we are merging our current state, so RAX, RDX, RDX, right, the current state, into this assumed state. And this means that we need to move the register RDX into RCX, right? So we are transferring our current state to the assumed state at the point where we want to jump to. So this is the code that's being generated at that point. It's a single mof. And then that's not a jump equals 0, that's a jump. Sorry. So this should just be an unconditional jump to the continuation at that point. And the continuation, this is the point that we will bind at the endpoint. So this is, again, an unbound label. Okay, now we see the else. Next thing. So now we are using this information that we kept before, right? So we are restoring the state from the beginning of the if. We are copying this into our current state. And now we are also binding this else label, right? So we have found the place where the if should jump if the value was not equal or was equal to 0. So we generate this code, and then we go on executing the code in the else. So in this case, an i32 const with the value 42. We just push this on the operand stack. And then, again, this block is done, and we need to merge our current state into the assumed state at the end. And this means that the value 42 needs to be moved into the register RCX. So we emit code for that, a single move instruction. Now we are hitting the end of the if. So now we are actually restoring or copying back the assumed state at that point into our current state, right? We now want to generate the code that follows the if, right? And everyone who jumped there made sure that the values are stored in RAX, RDX, and RCX. So this is the state that they can assume now in order to generate the following code. And the following code is a return. So what the return does is, it knows, because it's valid code, that there must be an int32 constant, int32 value on the stack. So in this case, it's an RCX, so it moves it into the return register, RAX, and returns. Okay, someone still following? Yeah, okay, cool. You can tell me later if this was interesting or useful. I'm open to feedback. Okay, so the code that we generated, if we just paste together all these gray bubbles, is this code. And this is actually what Liftoff would generate for this. So it's quite similar to the optimal code. It just contains a few more mofs, right? So we are first moving RDX into RCX, then jumping to the continuation, and then moving it into RAX. Turbofan would immediately move RDX into RCX. Yeah, this jump equals 0 to the continuation is again an unconditional jump. I will fix this. So this is more or less the optimal code, but it contains 2 more move instructions that are not needed. Okay, so for this baseline compiler, I can actually show you actual performance numbers because we now implemented this for real. So instead of showing you prototype performance numbers, I can show you immediately how it looks like. So these are numbers that we generated while I implemented the first version of Liftoff for the x64 platform. So on the upper half, you see the number of functions that are compiled with Liftoff. versus the number of functions that are still compiled with turbofan. So during the development of Liftoff, Liftoff was not able to compile all the functions. So it would only compile the functions that it fully supports, and whenever it hits some instruction that is not implemented yet, it just falls back to turbofan. And of course, yeah, by now we reached 0, so now all functions are supported by Liftoff. And what you see in the lower half is that while more and more functions are compiled with Liftoff, the compile time drops significantly. So by now, Liftoff is about 10x faster than turbofan. The runtime, so the quality of the generated code. Yeah, so while more and more functions are compiled with Liftoff, the code gets slower and slower. So, but only about 50% slower. So not too bad. And also the code size increases a bit because we have all these additional move instructions also for spilling more values to the stack and reloading them. So it's basically all the runtime regression and code size increase, or let's say most of that is just because we don't do a very good register allocation. We do the worst register allocation you can do. But if you want to have a single pass compiler, there is not much you can do, right? You don't know about the future uses of a value. So you generate a value, you choose any register. And if this value later is used in a call, for example, where it has to be in a very specific register, then, well, you have to move it there, right? But you cannot make this decision earlier. So yeah, there is not really a choice. So the code is about 50% bigger, which is still acceptable, right? These are some more graphs from the blog post that you might have seen. So on a MacBook, we ran 4 different benchmarks or demos for WebAssembly, so bigger stuff like AutoCAD. And it compiles about 8 to 10x faster than turbofan. If we execute the code, so this is the PS-PDF-Kit benchmark, also very interesting. So here I chose a configuration where I run all the code only in Liftoff, right? I basically disable turbofan. So we only run Liftoff code and we never switch to turbofan. And then the first 4 numbers are execution numbers, where the benchmark does operations on a PDF document. And this is about 30 to 50% slower than Liftoff code. So also not too bad. And then the 5th number, so the initialized number, so this actually measures how long it takes to instantiate a WebAssembly module. This is not only compilation, it contains a bit more, but still this number dropped by 56 on a desktop machine. Yeah, sorry, I didn't mention this. This is on 2 different machines. A Z840 is a big desktop machine, and a MacBook is a MacBook. And the initialization time dropped by 60 to 80%. And even overall, so the total score is just the sum over all these operations. So it basically executes all the operations and just takes the total time. Even that dropped significantly. Cool. Unity. On Unity, it doesn't look that good. It's a bit worse. So there are numbers that are above 100%. So this means that Liftoff takes more than 2x the time that it takes to execute the turbofan code. So the code is significantly worse. There are other cases where it's still around 30, 50%. And there's even this one nice case where the Liftoff code is actually faster than the turbofan code. So we fixed this by now by improving the turbofan code. So Liftoff actually helped us here to find possible improvements in turbofan, because Liftoff shouldn't be faster than the turbofan. If that's the case, then there's something wrong in turbofan. Cool. So the current status, Liftoff is now enabled by default since milestone 62. So this was released in September, I think. So it's enabled on Intel platforms, so IA32 and x64. We have ports for MIPS, MIPS64, and ARM. And we are working on a port, ARM64 is finished, and we are working on a port to ARM. So once this is done, we can also enable Liftoff on mobile platforms. But before that, there is one thing, and this is the last thing I want to talk about, one little thing that we need to optimize a bit. So if we look at the tiering strategy, which is basically the strategy we use for combining Liftoff and turbofan and how we choose when to run which compiler and which code, what we currently do is when we start compilation, we compile all the functions with Liftoff in the background in parallel. Once this is done, you actually get the module returned to JavaScript. So then you can work with the module. So you can instantiate it on the main thread and you can start running it. So yeah, in this execution phase, the lighter green is Liftoff execution and the darker green is turbofan execution. Because what happens is that as soon as we finished compiling everything with Liftoff, we will already start compiling everything with turbofan. So this happens in the background, but whenever a function is finished with turbofan, we immediately swap it in, so you will immediately execute the turbofan code from that point on. So basically your execution starts in Liftoff, and then it gets faster and faster as we compile more code with turbofan. Okay. So currently we just compile everything. So this can probably be done a bit better, and we are working on improving that. Right? But this is the first tiering strategy we started with, and yeah, for launching this is good enough. So you get this short startup pause, then you have this phase where you can already execute, but it's a bit unstable, which basically just means it's a bit slower. So you execute Liftoff code in the beginning and then more and more turbofan. But at some point, you have all code compiled with turbofan, and from that point on, you will be fast. Yeah, you can also see this. I don't know if many of you, so this is a Chrome tracing output, very cool tool. If you look at this, then you see exactly the same. So here the time is not from top to bottom, but from left to right. And you see all this Liftoff compilation and background tasks. So this is actually a number of individual tasks, but it looks like one block here. So this pink block is a Liftoff compilation. And once this is done, we can already instantiate on the main thread. So the first thread is the main thread. And after that, we start executing the code. And while the code is executing, turbofan compilation is running. So this is a nice visualization of that from real. So you see that it's the Epic Zen Garden demo in the second tab. Yeah, and the main problem with that is that we now generate each code twice. So we also need to store each code twice. So we generate it first with Liftoff, and that code is bigger than the turbofan code. And then additionally, we add the turbofan code. So this increases the memory consumption by about a factor of 2.5. Right? So it takes 1.5, the original consumption, just for the Liftoff code because it's bigger. And then we still add the turbofan code. And for desktop machines, this is okay because usually you have enough memory. So we are talking about a few hundred megabytes that we sometimes generate. So for this 40 megabytes WASM binary, we easily generate like 300-400 megabytes machine code. But on a mobile device, this doesn't really work. So for a mobile device, we are imagining something more like this. So again, a lazy compilation scheme. So you don't have any startup pause. And then when you hit functions on the main thread, you just compile them on the main thread. So lazy compilation with Liftoff on the main thread. Similar to the lazy compilation thing I showed before, but in this case with Liftoff. So your compilation pauses will be way shorter because we are compiling with Liftoff on the main thread. And then once a function gets hot, we spawn turbofan execution in the background. So this might be a scheme that works for mobile devices. It is not perfect because you now again have compilation pauses and it takes some time to have the turbofan code running. But if you are limited in memory, I mean, we just cannot hold all the machine code in memory. So we have to do some lazy and dynamic tiering. And so this still needs to be implemented. And once this is done and the ARM port is done, then we can also enable Liftoff on mobile. And this is the last slide I wanted to show. So I'll just leave this here and answer more questions if you have any. Yeah.
Is turbofan can reuse any of the resources generated by Liftoff?
No, it's completely separate. So turbofan needs to work on this sea of nodes and this intermediate representation, and we never generate this in Liftoff. So we don't have any intermediate representation. We immediately output code. So turbofan starts from scratch.
Could you optimize the Liftoff code when it's done and read just that code and not recompile it with turbofan, which uses...
We could do something like people optimization. So if we move something into one register and then immediately to another register, we could try to optimize this. So like looking at consecutive instructions and try to optimize them. But this is not something we are considering currently. So if you want to do it correctly, you would have to have another intermediate representation. So you create another, like a list of instructions that you want to emit. Then you run optimizations on this list, and then you emit it. And then we would again be a lot slower. So yeah, already because we don't have this streaming thing, right? So it's really nice to have the data fed in from one side and code out emitted on the other side, especially on memory-bound devices. This gives you a huge advantage. And if you generate an intermediate representation and iterate over that a few times and optimize things, then we lose the fast compile time of Liftoff. Yeah, so we are not considering that. So there was another,
This main thread, is this bound to one core, or can its main thread work on several cores?
No, the main thread is it's not bound to one core, but it is one thread. So it can be executed on another core, but it's still one thread.
No, not a core, but a single core.
It's a single thread executed on a single core.
So that's why my question. Normally nowadays you have 4, 6, 8 cores. Why don't you run on one core? Is it one compilation and on the other core another compilation?
Yeah. So of course, so instead of just executing all the Liftoff compilations first and only then executing turbofan, we could execute them at the same time, but then it would take longer until the Liftoff code is finished. Right. So we want to finish the Liftoff code as soon as possible. So we use all resources to compile Liftoff.
Yeah, but you can only use one core for that.
No. So this background compilation happens on a number of cores. This is why there are several lines next to each other.
Okay.
So compilation happens on several cores. And then we have the main thread, which is the most, so the leftmost.
Yeah.
So, 2 questions. One, how do you structure your code around this like different architectures? So you can immediately generate assembly, and usually this is done by having like a certain backend like that takes IR and then produces it, which is simple. But here it feels like it's very deep in your code, like even inside your business logic. Like how do you separate this inside your code?
Yeah, so the code is split between platform-specific code and platform-independent code. So there's an interface between this. So basically, what the platform-dependent code needs to provide is for each WASM operation, it provides an implementation for that. So we call a function that should emit an int32 addition of register A, register B, and target register C. And then different platforms implement this differently. But everything else, like this cache state, or the state management and the blocks, and this is all platform independent. So all you are implementing in the platform dependent part is really the generation of the instructions themselves. Right? So like emit a call, and these 5 registers are your inputs, or emit a conditional branch, this is your value and this is your target. And then, so it's mostly a few lines of code per WASM operation that you need to implement for a specific platform.
And I guess because Webassembly was designed with modern hardware in mind, there was no like bottleneck where like implementing one certain instruction wasn't really efficient this way, or like in a
it works quite well. Okay. Yeah. So I mean we can always make the interface a bit more complex to handle special cases. So currently we focused on having a clean separation between platform specific and platform independent code. If it turns out that this is a limitation, we can always, for specific operations, implement more in the platform specific code.
Yeah, you talked about 2 different strategies for mobile and I don't know how to call it.
Desktop machines, yeah.
Can also be a laptop maybe. So isn't that the right strategy? Because you have nowadays mobiles with 6 gigabyte of RAM, and I think the main issue is the memory available and not the platform which is running.
Yeah, so maybe the separation is not perfect currently. So we enabled on Intel platforms and only on desktop. So this is the configuration that we chose for now. Because for Intel it's implemented, so it's working. And for desktop, we just assume that there is enough memory there.
What is enough? Because we are working on Intel with very restricted memory.
Yeah, so maybe once we hit those cases, so we are collecting data about that, and if we see that the number of out-of-memory crashes, for example, increases, then if we see that this is Liftoff, then we might just adapt the strategy. Currently it seems to work. So I didn't see any spike in out-of-memories. Yeah.
Have you kind of measured what part of the worseness of the Liftoff code comes from?
No, so this is something I'm currently working on, and I will work more on in the future. So currently we are focusing on getting this feature complete and shipping it on all platforms, and then we can still optimize it. Yeah. So the first prototype we had was about 25x faster than turbofan, but it only implemented a few instructions, so maybe that doesn't generalize. And now the final implementation we have is only 10x faster. So there's probably some room for improvement. But I didn't spend a lot of time working on that yet. So
No, I was thinking more about the generated code. Because I
also
imagine
this
these are all toy examples, but it seems
Yeah.
so promising if you're only a little worse, no? With another.
Yeah, so probably the interesting cases are not those where we are just a little bit worse, but we will probably start by looking at the cases where we are a lot worse and fixing them. And at the end, we can probably generate better code, sure. But then again, we have to make sure that we don't increase the compile time. So this is the main focus: generate code as fast as possible, and the code quality is secondary. So if we can generate better code within the same time, then sure, we should do that. But we don't want to regress on the compile time.
So in this janky, slower phase, I'm thinking about like graphics stuff. Could it, stutter a bit?
Yeah.
Will we get something like an event or something to listen to that we know, okay, everything is optimized by now, and now we show the real...
No, so this is something we usually don't want to do, because this binds us to a very specific compilation strategy. So if we later want to change how we compile code, then this event doesn't make any sense anymore. So we usually don't add these events. What we are discussing is having a separate section in the WASM module that allows the developer to specify which functions are important, and then we can compile those functions up front. So in the startup phase, we would compile all the functions where it's encoded in the module that these functions are really important and we should compile them first. And the rest might be compiled just in time.
Okay, so I could run a version that I wanted to have compiled and see from there that it's already okay or better optimized.
So I'm not sure if I get what you mean.
I just want to know if there's some way to get there, that I know when everything's optimized that I need.
No, so depending on the strategy. So here in this right tiering strategy, there is no point where everything is compiled, right? Because there is not enough memory to store all the code in memory. So we might even remove code that we compiled with Liftoff. We might remove it later, or even turbofan code, because we run out of memory and then we need to recompile it later. So we never reach a state where everything is compiled. So this is something where you as a developer should trust the engine to do the right thing. Right? So it's our job to compile your code as efficiently as possible and have as little junk as possible. So this shouldn't be your concern. Or was there another question before? I don't know. Yeah, from that side. Yeah.
You can go in there.
No, I've already asked some questions.
And we are running a
bit
lot
late, yeah.
behind the schedule already. So
Question is quick. Like, how about we as the developers to be able to give some hints to the compiler what functions are important for us?
Yeah, so this is what's currently being discussed. So this needs to be standardized, so all the different engines understand this information, but then we can encode it in the WASM module itself. So this can either be done manually, or you could also have some profiling tool or something that does that automatically. So this would be part of the tool chain for compiling your WASM binary.
I thought I would be innovative by giving this idea.
No, unfortunately not. So we are just discussing this with our partners. It's not so we are not already implementing something. So this will take a while until this is done.
Okay, so let's have a 5 to 10 minutes break. Thank you.
And then we'll see.